Greetings and welcome back to another webisode of Good Idea, Bad Idea. Today we'll be investigating the question of dating dead things. Would you say that dating dead things is a pernicious personality problem or simply solid science? And our expert here today to tell you is Dr. Schuster. Simply solid science, he says. Here's the first question to investigate this issue. Yo, you just found a pottery shard and it contains 1 gram of carbon. Its activity is 0.0231 becquerels. How old is it? And you are about to find out because you are about to start dating dead things. So here we go. You need a little bit of background before you can do that. And that is that carbon-14 is radioactive. Also, it is produced in the upper atmosphere and captured in predictable amounts by things that are alive. What do you think? By CO2? I don't know, probably. Plants capture carbon-14, and when they die, the percentage of carbon-14 in them is given by this equation. It's a very small percentage, 10 to the negative 12th. Wow, so almost all of them is carbon-12, but because there's some carbon-14 in the atmosphere, they're absorbing that just as well through their CO2. Oh, the other thing that you need to know is that a becquerel is a unit of activity. And it's, well, it's sort of a decay thing. And it's in actually decays per second. And so that, I guess, means it's lambda times n. That's what activity is. That's what we're going to call aura, the decay rate. So it's, sorry, this is the decay constant times the amount that we've got at that time, and that's going to give us the decay rate. Next up, we need to know, where are we? Oh, right, the half-life, T1/2 of carbon-12. Where do I put that? 14, so, sorry, carbon-14 half-life is, oh, I can make another subscript there, that'd be fun, is 5,730 years. Wow, okay, so what we're about to do is find the initial activity of the carbon sample, and that will be called, oh, seafoam green, we're having a good time now, R0. Here is our quest to find the initial activity of our sample of 1 gram of carbon, back when it was originally dead, and then we'll be able to investigate our current activity of that sample and figure out some things about it. Here's what I say first. 12 grams of carbon-12. Well, we know some things about Avogadro or something. That means that we've got 6.02 times 10 to the 23rd atoms. And that means that 1 gram probably has 6.02 times 10 to the 23rd divided by 12 atoms. And I'll give you that number right there so you don't have to do it. 5.02 times 10 to the 22nd atoms of carbon-12. But if you've got that much carbon-12, you know that you've got, multiplied by this much, carbon-14. So we'll multiply those two numbers, and if we do that, you're ready to find out how much carbon-14 we have? 1 gram sample started with, here we go, this is very important, it's not going to have it afterwards because once the plant dies, it's not exchanging carbon-14 and carbon-12 in its respiration cycle. Do plants respirate? I don't even know. Ask a biologist. But the 1 gram sample pottery shard, it had that much carbon in it, and it started with exactly how many atoms of carbon-14? Let's see. I'm going to take 5.02 times 10 to the 22nd atoms and multiply by the percentage of the atoms that are, sorry, the fraction of the atoms that are actually carbon 14, right? That's a small number. Where is that small number? I know I have it written down somewhere. 1.2 times 10 to the negative 12th. And that gives me, 6.02 times 10 to the 10th atoms, 10 to the 10th atoms of carbon-14. That's what we're starting with, and it's a pretty big number. What's that, 60 billion? Yeah, we're still cool. Okay, we can look at that for a few thousand years. So, here's the thing. We've got that much, and now we need the decay constant. Decay constant. We're off on a quest for the decay constant, and the decay constant is lambda. And here's how our quest begins. Lambda is the natural log of 2 divided by the half-life. But we better convert the half-life into into seconds so that we're in SI units and everything is fair. This is about 0.693, and then I'm going to divide it by 5,730 years, and that's the same thing as 0.693 divided by 1.81 times 10 to the 11th seconds. So this lambda is going to be a pretty small number. It turns out that it's 3.83 times 10 to the negative 12th 1 over seconds. Interesting. So it's not very common for a carbon-14 to decay into a carbon-12. So let's get our little rate here. We're looking ultimately for the, remember we started here, we're looking for the initial activity. And the activity is, initially the activity is lambda times the initial number of those suckers right there. So we can multiply these guys. We've got lambda right here, and we've got the original number right here. So I'll plug this guy in here. And when I multiply those two suckers, not to bore you, I'm going to get 0.231. And it has units of number per second, which is the same thing as a freaking becquerel. And this is an interesting time to remind ourselves that our activity right now is 0.0231 becquerel. Oh, Dr. Schuster, I see what you did right there. So, if, here's my statement, if the activity now is the original activity times the exponential, lambda t right there. Oh, why can we say that? We can say that because we know that the original activity is just lambda times n naught. And everybody knows that activity is lambda times m naught, n naught times e to the minus lambda t, because the definition of activity is, I think they said that activity is lambda times n, and this is n at any moment in time. So this is a reasonable statement, and then we can just solve this. Ultimately, I'm trying to solve this sucker for t. Watch this. I'm going to say r over r naught is e to the negative lambda t. I'm going to lean in a little bit and whisper at you because I'm trying to get t on its own. I have to attack with the natural log. It's the only way to kill that exponential. The natural log of this ratio, r over r naught. Can we just get a what on what the heck this is? R over r naught for us. We said that the activity had dropped by a factor of 10, so this is just 1/10, and we'll be able to plug that in. This is just for us right here. And this is negative lambda times t, and I guess I'm going to be interested in finding t, as I promised. T is the natural log of that ratio, r over r naught, then divided by negative lambda. I'm about to plug in all these numbers, and it's going to be absolutely disgusting, but here we go. I'm going to plug in the natural log of 1/10, and then I'm going to divide that by lambda negative, oh shoot, the natural log of 1/10 divided by, and now I need that decay rate again. I think, here it is, here's the decay rate, 3.83 times 10 to the negative 12th 1 over seconds. So this is not going to be a happy time. Let's do this. Natural log of 1/10, and then I divide it by negative 3.83 times, where's my 8? Oh, shoot, 83 times 10 to the negative 12th. I hit enter right there, and I get, oh my goodness, that's a very long time. 6.0119 7 seconds. But wait, we're not interested in seconds, right? So let's see how many minutes it is. Oh, it's that many minutes. That's still a lot of minutes. Let's see how many hours it is. Oh, it's that many hours. It's still a lot of hours. Oh, how many days is it? That many days. Dang, let's go to years. Wow. So we're talking about 19,000 and then another 63 years. I see another way to do this though, because what's interesting about this is I'm going to figure out how many half-lives that was. Remember we said that the half-life of carbon is 5,730 years? It looks like it's 3.327 half-lives. And I see a shortcut, and the shortcut is this. As soon as you know, wait a sec, let's just reflect that we found a pottery shard that's almost 20,000 years old. So that's cool. We should call somebody about that, especially if it's in America. That would be some interesting data somebody needs to know. But if we've got 3.327 half-lives, and that means that we have 1/10 as much activity, shoot, if you know this right here, then you can find out how many half-lives have gone by. What if we knew that R over R naught were 1/8? ... How many powers of 2 do you need to get to be 8? ... Do you see why it's 3.3 or so half-lives? I guess if you know a lot about logarithms, you can do this in an incredibly fast way. You know, bloga and all that stuff? I don't know anything about that, but maybe you've studied it. Goodbye. Gram of carbon. Its activity is 0.0231 becquerels. How old is it? And you are about to find out because you are about to start dating dead things. So here we go. You need to, I don't know, probably, plants capture carbon-14, and when they die, the percentage of carbon-14 in them is given by this equation. It's a very small percentage, 10 to the negative 12th. Wow. Greetings and welcome back to another webisode of Good Idea, Bad Idea. Today we'll be investigating the question of dating dead things. Would you say that dating dead things is a pernicious personality problem or simply solid science? And our expert here today to tell you is Dr. Schuster. Simply solid science, he says. Here's the first question to investigate this issue. Yo, you just found a pottery shard and it contains 1 gram. A little bit of background before you can do that, and that is that carbon-14 is radioactive. Also, it is produced in the upper atmosphere and captured in predictable amounts by things that are alive. What do you think? By CO2.